Okay, and I have turned on the record button. I know I recorded a few lectures earlier in the semester. I'm going to try doing that again. Um, uh, I'm going to do it directly with my Doceri app, and so it'll look like the times before. It won't be the recording of the Zoom session. So hopefully it'll work that way. Let me get a couple things going here that I need. So of course you can always raise your hand, submit a question via the Zoom chat function or however you want to do it. What we're going to talk about today are derivatives of trigonometric functions. And so there's a few things that we have to talk about beforehand. You all know how limits work, and limits with trigonometric functions are really no different, except that we have a few special limits that come about beyond methods that we would use in class, other than plugging in numbers and then getting closer and closer and closer to the value that you're trying to find the limit of. And so some very special limits come out of this. The sine of x over x, if you think about what the sine of 0 is, that's 0, and the sine of x is, just as x goes to 0 is 0, you have that 0 over 0 form, and that actually goes to 1, the ratio of 1. And your book has a discussion on that. I'm not going to ask questions about how you prove that. I just want you to be aware that that is what that limit is. And then the limit as the cosine of x minus 1 over x, there again you'd have the 0 over 0 form, but this limit turns out to be 0. So be sure you read the text to see how that comes about, and we're not going to take any class time in going over that. The third limit that's on there is the limit of 1 plus x to the 1 over x. Now, this is a important financial limit that basically takes compound interest formulas and lets you get a function that you can calculate continuous interest from. And so you could see as x goes to 0, 1 plus 0 is 0, so you have 1, or is 1, so you have 1 to the 1 over 0, which is not a number power. And that's one of the magical places where e shows up. And so it's actually kind of a difficult thing to show with just the methods that we have. If you ever when you take Math 38, you'll be doing some infinite sequences and series. And so there is a power function that actually demonstrates that particular limit. So you'll wait a couple semesters on getting to that one. And then the fourth one is e to the x minus 1 over x, that is as x goes to 0, and you can see that that's that 0 over 0 form if you just plug in x. And but then again, if we take and this uses an infinite series as well, we get that limit to be equal to 1. So just so you're aware that there are some special limits that involve both exponential functions and trigonometric functions. Okay, so let's get into derivatives of trig functions now. One of the things that we're going to make an assumption of is that the derivative of the sine of x is the cosine of x. And hopefully you can kind of qualitatively see that. If I take, let's say, a graph of the sine of x, it looks like this, of course. And at least to make it seem plausible, you can see the derivative when x equals 0 looks like it's 1, and the derivative when x equals pi over 2 is 0, and then the derivative when x equals pi is negative 1, and then at 3 pi over 2, you have the derivative is 0 again, and so and then at 2 pi, which is right here, the derivative is back to 1. And so if I make a curve here, you can see that that looks like the cosine. Now certainly that's not a proof that the cosine or that the derivative of the sine is a cosine. But hopefully, at least it seems plausible to you that that's the case. Now we can do the other direction where we say the derivative of the cosine, and if you do the same kind of thing by taking a cosine graph, and you say, okay, when x is 0, your derivative is 0. But then here in the cosine, when we have pi over 2, the derivative is -1. And so you're going to get that sine curve again, but it's going to be negative. So the feature of that derivative of the cosine is that it's the negative sign. Okay, so for all the rest of the functions, what we're going to do is make use of the quotient rule. But before we get to that, let me make a comment about taking the derivative of the sine is the cosine. Take the derivative then of the cosine is going to be negative sine. The derivative of the negative sine is negative cosine, and the derivative of negative cosine of x equals sine. So here we have kind of a periodic nature of when we take progressive derivatives that we get. The derivative of sine is cosine, derivative of cosine is negative sine, derivative of negative sine is negative cosine, derivative of negative cosine is sine. So we have that kind of cyclical behavior, and that's just by the nature of the fact that sine and cosine are repeating functions. All right, so let me remove some of that. Now, the derivatives of the other trig functions are going to be, oops. Oh, sorry about that. Here. Oh, I hope I didn't destroy that. Anyway, well, I'll just recreate it. This is going to be, of course, over g squared. So we're going to make use of the quotient rule to get the other derivatives, because you remember that the one that we're missing here is tangent, and the tangent of x is the sine of x over the cosine of x. So we can find the derivative of that using the quotient rule. And then also with the secant, the cosecant, and the cotangent, those are all reciprocals of sine, cosine, and tangent. So we'll be able to get all the derivatives that way. Okay, so the derivative of the tangent is the derivative of the cosine of the sine of x over the sine of x over the cosine of x. Okay, it looks like I'm going a little bit ahead of you guys. What's the derivative of negative cosine of x? Yeah, it is the sine of x. So it just keeps on going around. Thank you, Sidonia, for answering to the group that way. All right, so let's look at the derivative of tangent. So we'll make use of the quotient rule. So what we have is the derivative of sine is the cosine times the cosine, which is the denominator. And then we have the sine of x, which is the numerator, times negative sine of x, which is the derivative of the denominator, cosine, all over cosine squared. And so we see that when we make them squareds and we cancel out the negatives, we get the cosine of x, cosine squared of x plus the sine squared of x. And by our identities, of course, that equals 1. And so the derivative is 1 over the cosine squared of x. 1 over the cosine squared of x is, of course, the secant squared of x. Now, one of the things that you'll notice, and perhaps you have already, but the tangent and the secant always seem to show up in pairs, and the cotangent and the cosecant show up in pairs as well. So let's look at the derivative of the cotangent. Now, it's a similar kind of thing to the cosine over the sine of x. we're going to take the derivative of the cosine, which is negative sine, times the denominator, which is the sine of x. And then we're going to keep the cosine, and then take the derivative of sine, which is cosine. And if we notice that we have two negatives here, what we get is that same kind of thing at the on the numerator, where we have the sine squared of x plus the cosine squared of x is 1, but both of them are negative, so we have negative 1. And you'll notice that the cosecant, the negative cosecant squared, will be the derivative of the cotangent. Now, one of the things I'd like you to notice is that all the cofunctions, like cotangent, cosine, and we'll see soon here that the cosecant, always start out negative. So that's just one thing to help you remember what these formulas are. So let's do the secant now. So the secant, of course, is the derivative of 1 over the cosine. So let's use the quotient rule there. And we see that the derivative of 1 from the numerator is 0 times the denominator, cosine. And then we have minus the numerator, which is 1, times the derivative of the denominator, which is negative sine. And so if we simplify that, what we get is the sine of x over the cosine squared of x. Now, the form that we usually like to have that in is to separate the cosine squared into two factors of it, and you'll see then that that equals the tangent of x times the secant of x. And so that's, again, stating this in those pairs of functions, tangent and secant go together, so we don't start mixing up a lot of different functions. So it's not wrong to use the sine of x over the cosine squared of x as the derivative of secant of x, but ultimately you'll find it a lot easier and a lot more uniform with the work that you're doing if you take the derivative of the secant in terms of the tangent and the secant. Okay, and then we have one more, which is the cosecant, and that's the derivative of 1 over sine. And so the derivative of 1 is 0 times the sine of x minus 1 from the numerator times the derivative of the denominator, sine, which is cosine. And so, and then that's over the denominator squared, the sine squared of x. And so we get negative cosine over sine squared of x. And if we state that first by separating the sine of x, what we get is the negative cotangent times the cosecant equals the derivative of the cosecant. Now sometimes you see it written, these two written in the opposite order, where it's the secant of x times the tangent of x and the negative cosecant of x times the cotangent of x. Those are all the same, right? It's just the commutative property of multiplication. So you'll see them in both ways. There's no real standard way to do these. Okay, any questions so far? So one of the things that that you have to do is to remember all these things, and I think it's easy enough to remember the derivative of the sine is cosine, the derivative of cosine, since it's a cofunction, is a negative sine. The other four, the tangent, cotangent, secant, and cosecant, if you just remember how to derive them, it's a little bit of writing, but it's okay to remember how you get to them rather than the actual function. And in fact, that's the way I do it. If I've gone a long period of time without doing any calculus with trig functions, the first time I encounter it, just to kind of confirm to myself that I'm remembering it right, is that I do the derivation. So you might think that that's a lot of writing or whatever, but it is a sure-footed way of getting to the derivatives. And then always remember that the cosecant and the cotangent and the secant and the tangent are always paired, and then it makes for a little easier thing to remember. And of course, all the co-functions have negative derivatives. Okay, so here's the summary of the functions that, the derivatives of the functions. And so what we have to do here is make a couple mental notes, things that I've already talked about. All the cofunctions have negative derivatives, and the tangent and secant show up together, and so do the cotangent and cosecant. They show up together. And you do have to have this table memorized. So it's not, once you get some practice, it's not too bad. Okay, so let's kind of forge ahead, unless there's some questions. Okay, so let's do some practice. Why don't you, we're going to get to progressively more difficult derivatives. So let's everybody do this, and I'm going to give you a couple minutes on this to do, and then we'll go on to some others. If you're looking at the Isabella, you want to go back just a minute. If you want to you kind of look ahead, of course, you can work ahead on these, but I'd like to kind of pace through these just so we don't leave anybody behind. I'll give you a couple minutes here to do this one. This shouldn't present too much of a difficulty. Okay, so that should be plenty long here. So here we just take the derivative as the first term is going to be 6x, and then the second term we have the derivative of the cosine, which is the negative sign, so that negative will become positive, and we have 2 sine of x. Okay? I don't see it showing up. I think my internet connection's a little unstable here. Let me reset this. Okay. So let's do the next one now. Oh boy, this is not moving. Okay, so there's the second one, 2 cosecant of x plus 5 cosine of x. See how that one works for you. I'll make myself some room here. Okay, so let's look at this. We have y prime equals, so the derivative of the cosecant, remember, is negative. We'll keep the coefficient, so that's cosecant x cotangent x, and then the derivative of 5 cosine is going to be negative 5 sine of x. And there's really no need to change it around too much. We have a bunch of identities and things that if we're trying to solve problems, then perhaps restating it in terms of just cosecant, like making that negative 5 over the cosecant of x, that may be worthwhile, but it's certainly not necessary just for finding derivatives. Okay, so the next one is going to just be y equals a sine of x plus 1/2 the cotangent of x. And I'll give you just a couple minutes here to do this. No, Jonah Lee, you're right. You have negative 2 cotangent of x, cosecant of x. The order between the cosecant and the cotangent don't matter. That's commutative. So I guess I put cosecant of x, cotangent of x, just that's kind of the way I'm used to writing those, but either order is wrong. Is right, not wrong. Okay, so this should be some direct substitution as well. So what we get, whoops, is y prime, the derivative of sine is cosine of x. The derivative of cotangent is negative 1/2 cosecant squared of x. Okay, so Jonah Lee, you're asking about parentheses again. When you just have a simple variable like x, it's not really that important. Sometimes, I guess to be absolutely proper about it, you should put parentheses around your angles. There's really no need to put parentheses around the cosecant and the cotangent of x. That's understood that those are multiplied with each other. So it's possible to overuse parentheses. Other times, if it makes it clear, you feel free to use them, but they're certainly not required. Okay, so after this, what I'd like to do is give you the rest of them, and give me a yes when you're done with this, and then we'll go over these individually. So this might take a few minutes, so go ahead and work on these. Now remember that a lot of these will take things like the product rule. I guess these will take the product rule and the quotient rule. We don't have any chain rule things yet. Okay, so let's see how these work out. So the square root of x sine of x, we're going to make use of the product rule. So that's going to be 1/2 x to the minus 1/2 sine of x. That's the first part. Then we're going to add the square root of x times the derivative of the sine of x, which is the cosine of x. The second one, we get a little bit more complicated here. The derivative of the secant is going to be the secant of x tangent of x times the tangent of x plus the secant of x times the secant squared of x. And so if we were to simplify that, we can say that this is the secant squared, or excuse me, just the secant of x times the tangent squared of x plus the secant cubed of x. So that's a little simplified way to do it. Notice that we can also factor out the a secant of x, and so what we get is the secant of x times the tangent squared of x plus the secant squared of x. So whatever ends up to be convenient there. I'm going to just preserve my space and keep the derivative without simplification there. Okay, so here we have one that involves an exponential function, and so the derivative of e to the x is simply e to the x, and then we keep the tangent of x minus x, and then we take the derivative of we keep the e to the x and take the derivative of the tangent, which is the secant squared of x, and then derivative of 1 is minus 1. So also notice that secant squared of x minus 1 can be, you can substitute a tangent squared of x in there to make it a little simpler, but for the purposes of this exercise, it's not really necessary. All right, and then the second to the last one is going to be negative 3 times the sine of x. And then here we have to use the product rule, 2x the sine of x plus x squared cosine of x. And so we gained a term by doing that. All right, so now this last one involves the quotient rule. So I think what I'm going to do is I'm going to copy this to a blank page. And then we'll do this with a little bit more room since it's a little bit more complicated. Okay, so the derivative by the quotient rule is going to be the derivative of the numerator. It's just going to be the cosine of x times the denominator. And I think I'm going to run out of room up here, so I'm going to move this. Minus then the numerator, times the derivative of the denominator, which is 1 minus the sine of x, and all of that is over x plus the cosine of x squared. Now let's simplify that numerator because we'll have an opportunity to cancel something in here. So we'll say this is going to be x cosine of x plus the cosine squared of x. That's from the first term. And then we have minus 1 minus the sine squared of x, if you look at these as being conjugates of each other. So, and that's over the same denominator. So if we distribute this negative, we have x cosine of x plus the cosine squared of x minus 1. And then what we have is plus the sine squared of x, and that's all over x plus the cosine of x squared. Ultimately, what we get then is that these two terms make 1, and we're subtracting 1, so all that cancels out, and we end up with just the cosine of x over x plus the cosine of x squared. Okay, so how's that? Any questions on any of these? Okay, so if we're all good, let's go on to the next one. So here we have a few that involve the chain rule and the quotient rule. Now it's about 20 past 11, and we won't have time to do quite all of these. So let me forge ahead a little bit, and then we'll come back to the practice. So if we look at where we're going to go, and we'll talk about this on Wednesday, the derivatives of trig inverse functions are going to make use of using that reference triangle. And so you can see from the bottom here that a derivative that we get from the arc sign is actually going to be an algebraic expression. So that's a little bit surprising, I think, the first time you see it. But once we walk through how how all this works, then then it'll start to make sense, to the point where we'll have the derivatives of the inverse trigonometric functions. Now, the thing is that these are kind of complicated, and I'm not gonna ask you to memorize these. We're going to do some work in them on Wednesday, but you'll always have these as a reference if I'm going to test you on them. So this is going to be basically really an exercise in substitution more than anything else. Okay, so that's what we're looking at on Wednesday. So let's go back to these problems, and let's say, for the interest in time, since we have 15 minutes, let's do the first one. And let's do the fourth one, okay? And I'll give you a few minutes to do that here, and then we'll look at the solutions of that, and then we'll go from there. See how much time we have. Let's see, it's 22 past, so I'm probably going to let this go maybe 5 minutes. Whenever we're doing written homework with derivatives, or tests for that matter, is to collect coefficients and do things like that, see if we can avoid compound fractions. But in general, no. If you have to take a second derivative, it's almost always to your benefit to take the second derivative, or to simplify before you take the second derivative, because you'll end up with a simpler problem. So I think the obvious stuff you should simplify, but you don't need to, find all the sine squared x's and cosine squared x's and eliminate them to 1 and things of that sort. Unless, of course, I give you some special directions as to what I'm looking for, but in general, no. Okay, so let's see how these derivatives will go. We'll look at the first one. Y prime is the derivative of the numerator. Uh-oh. Okay, so y prime is the derivative of the numerator, which is the derivative of secant, is the secant of x times the tangent of x, and then times the denominator, which is 1 plus the secant of x. And then we're going to subtract that from the numerator times the derivative of the denominator, which is going to be just the derivative of the secant, which is the secant of x tangent x. Sorry for my cramped writing here. All over 1 plus the secant of x squared. And if we do one round of simplification on there, we can see that the numerator distributes as the secant of x tangent of x plus the secant squared tangent of x, forgot my x in there, minus the secant squared of x tangent of x all over 1 plus the secant of x squared. And so you can see that this here drops out, and so what we get is essentially just the secant of x tangent of x over 1 plus the secant of x squared. Now, to that degree, I would like to see that simplification done where we just have terms that cancel out. So I think the expansion is worth just to see what drops out. Okay, then the very last one, we're looking at using the chain rule for the first time. So the derivative of the cosine is negative sine. Remember, we keep the inner function the same. And then we multiply it by the derivative of the inner function. Now, a is a constant, so we just, that's going to be 0. And then we have 3x squared. And so that's your that's the derivative there. So I would suggest you you look at these. I will be giving some homework on derivatives, and one of the tricky things that you'll need to kind of master is being able to use the chain rule with things like the derivative of the secant. You know, where you have two terms, the secant x tangent x, and we'll talk about that again on Wednesday. So. I'll be assigning a web work sometime this afternoon, and that's going to be probably due on Friday as well as the one that you have to turn it in, and that'll just be a web work to practice derivatives. Remember, we're not going to be doing the gateway in the usual sense that you're going to get on the on web work. I will have a derivative test, but that's going to be done a little differently. It's not going to be like a gateway, and it's not going to be scored like a gateway. I'll give more information on that on Wednesday, but you don't have to worry about how the gateway is going to happen for you. It's just going to be a matter of getting it tested within the course. Okay, so that's it for today. That's certainly enough. That's a lot to do. See if you can do the rest of these derivatives, and make sure you address the problems that we had, the general trigonometric problems, so we can talk about them on Wednesday as well. Okay, so that's it. Feel free to log off, and I'll talk to you all on Wednesday, if not before. I will do office hours by appointment over Zoom if you like.